Hello, this is Dr. Brothers. This video is going to cover simulation. Before I get into simulation, though, I want to ask you a question. What is design? So, as an engineer, one of the things that we're supposed to do is design and build stuff. But what is design? If you ask that question, you might think about, in the old days, a lot of engineers sitting at drafting tables, drawing parts. They might be drawing circuits, circuit design, or they might be drawing on CAD, doing mechanical design where they're drawing a part in 3D space on a computer. Or you might think of software design, where in software design you're going to make a software architecture, a software framework, or a software flow diagram where you have the software described via a picture. That's really what all of these are doing. We're describing something in a rendered fashion. But what we want to do in design is further than that. We don't want to just describe something. We don't want to just show something. We actually want to show that what we've designed is going to meet the requirements before we ever start to build something. So before we start to build, we want to make sure that our design is going to do what we expect it to do. And that's where simulation comes in. So let's look back and see what bookends design. So on one side of this phase, we've got requirements. So we have customer needs that go through some needs analysis, and that creates a system level, and then a subsystem level, and then a component level requirement. So through design, we're now going to draw out what we want each one of these stages to be. Before we start building anything, we're going to have it completely defined what it is we're building, and that's design. Let's look at it pictorially in this manner. Customer discovery and needs analysis, that's what I showed at the last screen. We're going to do system, subsystem, and component. Once we get the requirements, those are going to drive down into the design. The design is what we're going to focus on. We're going to capture what it is we're building and make sure that what we've captured is actually what we want to build before we ever start building. And that's really what sets an engineer aside from, say, a hobbyist. So we do decomposition, which is system, subsystem, component levels, and design. Design is drawing out what we want to build and making sure that it is what we want to build before we ever start building it. And then we're going to do build and test. Those two kind of go together because the whole time you're building, you're also going to be testing. So you build and test the components, you build and test the subsystem, you build and test the system. And you integrate and test as you go. So once you get one subsystem designed, you're going to put it together with another subsystem, you're going to integrate and again test. So what makes an engineer? I said this earlier. The difference between a hobbyist and an engineer is good design. So what we're going to do, we're going to design, we're going to simulate it. We're going to go back to design. We're going to simulate it. We're going to go back to design until we're confident that our design is going to meet the requirements. So before you ever start building, you need to have complete faith in your design. So if you have a circuit and you don't know whether your circuit's going to work or not when you put it down into the actual PCB, you're not ready to do the PCB. You're not done with design. So subsystem design. We're going to start. We have a system, subsystem, and components. Components for our applications we're going to buy off the shelf. So we're going to put those off-the-shelf components together into subsystems. For electrical, we might have digital systems, analog systems, motors, I/O devices such as LCD screens. We're going to have power. We need to power this whole thing. Mechanical, you can think about this. We might just have a mechanical sketch that we're going to start from. We might have a full-up CAD design. Software, we could start with a software architecture. We could have embedded software, networking software, user interface software. There's a whole world of different subsystems that we can build in isolation or design in isolation and make sure they're going to work before we ever start building them. Driving it all are the algorithms. The algorithms, we could just have an equation, a mathematical equation, or we can have some physics-based algorithm, such as radar. Radar is a great example. You have a transmitter, you have an object that's flying through the air, and you have propagation waves that are going to hit off the airplane and come back. how do you make sure before you start building your radar that that's going to work? How do you make sure the physics are going to work? The answer to that is simulations. So for electrical, here are some types of simulations that we can do. A breadboard simulation. We can take a breadboard and we can put something together. Here's a messy breadboard that I have on my bench right now. But here's a breadboard where we're testing out different things to make sure our design works before we actually go to build it. This isn't building it. I'm not going to put this in my box. But it's a simulation to make sure that it's going to work before the end. A SPICE model. We could put an analog circuit into a SPICE model and come out with a very high degree of confidence that it's going to work. Motor testing, same thing again. Here I have my motor hooked up. Maybe all we do is hook up the motor to the Arduino and run that. And once we do that, we're like, okay, we've simulated the motor. We showed that that works. It's not in a realistic environment. We might just be holding it with our hand. We might have some dummy load on it. We want to have confidence in our design before we start building. You could do processor emulators. So Tinkercad is a wonderful application if you're going to emulate the Arduino. There's not one for the Raspberry Pi that I've found yet, but emulators are great tools. Excel. We can use Excel to do things such as power budgets, link budgets, where all you're saying is, okay, here's how much power we have from the analog to digital, or from the AC/DC brick. You know, this brick coming into our system gives us so much DC power, so much wattage. And then we know that the motors pull so much, the processor pulls so much, the LCD pulls so much. And we can just add those numbers up. That's a great simulation to have confidence in your design. Mechanical CAD simulations. So a lot of the mechanical CAD tools have a simulate tool, function where you can actually move things around. Simple models. We are not mechanical engineers. I do not expect you to go out and do a full CAD simulation. So if you want to, take some pieces of wood, cut them, hammer them together, and say, okay, here's how it's going to work. And it's going to move like that. Make a big scale model. You might want to end up with something that looks like this, right? Something small that looks like this with laser printed things that are connected to the servos that are going to move the arms and move it around. This guy is really cool. He's got a whole framework that's holding the back of the penguin up, and it's moving the arms with these servos. But before doing all this, you can just make a mock-up and see if this is going to work. Legos. Legos are great, especially if you get the Legos that have the gears and pulleys and motors that can run them. So get some Legos and just put them together and see if your mechanical design will work. 3D printing. You've got to be careful with this one. This can be a rabbit hole that you get sucked into. You can say, hey, we're going to just quick 3D print this thing and try it and see if it works. And before you know it, you're just spending all your time 3D printing. Try to avoid 3D printing if you can. Do simpler things than 3D printing. All right, moving over to the software side. We can do a software framework. That just means that you have dummy functions that don't have anything inside them. Let me rephrase that. You should do a software framework. This should be, you should do a software architecture first, then a software framework second. Architecture is broad strokes. It's saying, okay, this function will talk to this function that'll talk to the motors. The framework is actual code, and it's just like skeleton code. That's nothing inside the function prototypes, but everything is there. This also makes it easier to use Git because then you can commit that framework into Git, and people can go in and fill in function prototypes. Breadboarding again. How do you check that the software is going to control the motors? How do you check that your microphone is going to get sound into the Arduino or into the Raspberry Pi? Breadboard it up, just that one component and the processor, and see if the software can read it. Test code. Everybody should have test code. You should start off, integrate this into your design. Know what you need to do, but also have test scenarios that are going to run to test things out. Algorithms, you could do mathematical derivations. You can do simulation models using something like Python or MATLAB to make sure that what you want to do is actually going to happen. All right, here's the time frame. This is what's important to your project. PDR, you need to have the initial design completed. That means you have to have back-of-the-napkin sketches. You need to have an idea what components you're going to use. CDR, you have to have all the simulations completed and the final design. Okay, so if we go back to this illustration, design, simulate, design, simulate. The very first design needs to be done by PDR, and then we're going to iterate this through again and again and again. And by the time that we get to CDR, you need to have completed all your simulations. All right, that's it. Please let me know if you have any questions on this.